Okay, I've started recording it. Now, I'm going to share my screen. Can you guys hear me okay?
Yeah. And how do you feel, Daryl?
Oh,
Yeah, yeah, we can see you.
yeah. Okay, one second. Let me turn off my telephone. My brother was calling me, and I need to just not be interrupted. So, all right. I feel good. Can you guys hear me? Okay,
Yes.
I feel good. This is a heavy lift. This session, unlike the last session, which I was very strong in my own practice. This session I usually use to partner with, but nevertheless, this is on quality, and I feel good and ready to get going. So I appreciate all you guys signing in and showing up all the time. So with that, I'm going to share my screen and we'll get going. Okay, one second, guys. Okay. Okay. Mhm. Okay, let me know if you guys could hear it. Can you see that screen? All right, so I'm gonna start this over. So you want to count how many times the white shirt people passes the ball. So this is an ad. I don't know how to get rid of this ad. Just bear with me. Oh, let me skip the ad. Let's see, skip the ad.
The monkey business illusion. Count how many times the players wearing white pass the ball. The correct answer is 16 passes.
So
Did you spot?
what did you guys notice?
Alvaro
That was a bit
walking
slow.
across.
Was it slow? Huh?
Yeah, it was sort of like choppy, no?
Yeah.
Don, what did you say?
I saw Alvaro.
Do you mean because of these?
No, it was really Alvaro all through from head to toe.
Have you guys seen that training video before?
Yeah, unfortunately, I've seen it before.
Okay,
I have to.
My brain was
yeah, I wasn't sure how many
predisposed.
people had seen it, but the question
Then
was,
ask the others. Ask the others. Ask the others.
how many
Okay.
people?
Anything unusual? Ask the
If-
anything unusual.
Anything unusual? Anybody who's not seen it? I forgot to preface it. Some people may have seen it already. Anyone see the gorilla that have never viewed this before?
Yes, I saw the gorilla.
No.
Yeah, I've seen the gorilla.
You guys are too smart. See. All right. Well, with that, we'll delve in. So the whole point of that exercise really is to impress upon folks that that whatever the task you're engaged in, how you go about doing the analysis, you are looking for things that are not necessarily as visible for the trained eye in the middle of what it is they're doing. So,
Wait, Daryl, just one question. There was a gorilla in the video you just passed?
yes.
Oh, I didn't see it at all. At all.
The other guys they've been exposed to the training in some way, shape, or form, and so usually, if you're just counting the balls passing, most of the time, when I first saw it, I didn't see the gorilla. I told the instructor, "Show that to me again." I can show it to you again, Jorge. But if you look up the hidden gorilla exercise on YouTube, you'll catch there's 3 or 4 different versions of it. Yeah, while the people were passing the ball around, there was a guy in a gorilla suit walked across, stopped in the middle of the group, and then he continued walking across. And if you've not seen it, before and be familiar with it, you may have missed it.
Well, hey, where I saw it was in a room of about 400 people.
Uh-huh.
And at the end of it, the person said, who saw something funny? And only about 10 people out of the 400. And when they replayed it, I couldn't believe it. So,
right.
yeah.
I know me. And same with me. I insisted to the instructor. There was no gorilla, but he played it. And sure enough. So anyway, Jorge, you could take the opportunity to look at it. It's called the Hidden Gorilla Exercise. It's pretty famous now since 2010. But anyway, I thought, this is a fun thing to do. And I should have figured as much as you guys get around, half of the group would have seen it. But the point is that when you're doing analysis, and today is be a little bit about analysis and improvement, or a lot of it. So in this, and I'm calling it, as I did last time, the mixed methodology approach, because like Vladimir shared with the client that he and Greg got, the question to them was, right before you guys came on, was how would Adizes methodology comport and be in collaboration with Lean? Because they had, as a production company, they want to do Lean. And he had a great answer in that, just so happens we're in the midst of doing some Lean training and collaborative design right now. So this is very much intended to be a collaborative approach. So I'll go on to the next slide. So data tools. So at the end of this session, and as always, guys, you could stop me anywhere and we could talk about things. At the end of this lesson, you'll be able to identify tools and methods to collect and analyze data. So there are essentially 7 data tools in this focus this week is really on quality, and this is the Six Sigma portion. And Lean is to ridding the organization of waste, as Six Sigma quality is ridding the organization of variation in their processes. To the degree your process is stable and repeatable, is a leading indicator that you actually have quality products built in. You have quality built into how you get things done. And these 7 quality tools were put together by one of the gurus of the whole Lean Six Sigma evolution, a guy named Hishikawa. Hishikawa is an interesting man because Hishikawa was part of the Nippon, I think that's how you say it, the Japanese telecom. It's a large telecom company in Japan. And although most of what you hear about Lean comes out of the Toyota production system, this man Hishikawa was significant in that he sort of laid down the law, much in the way Chuck Berry played guitar in the 50s and laid down the law in rock and roll, that everybody came after him had to do. If you were playing rock and roll, you had to pretty much do it in the manner and shape that was created by Chuck Berry. These tools, the check sheet, flow charts, histogram. Now, they may have been in the statistical practices beforehand, but to the point that they made a difference after scientific management, say World War II-ish sometime, Hishikawa stepped forward from the Nippon telecom company and sort of laid down the law in his book he wrote regarding the 7 tools of quality. Okay, and his book is entitled Introduction to Quality Control. Where it says here he identified 7 basic tools for quality control, and the key is he combined this work with the concepts of variation and statistical analysis. Nobody had done it before he did it, and he did it for the purposes of tightening up production kinds of operations. Okay, so it was used for essentially organizing and collecting facts in the data in order to help decision makers make better decisions. It's like you could fly blind and do things and kind of intuit your way through a process, and kind of your experience, your empirical observations always mattered. But it certainly made a difference when you could actually document, put on paper, in either real time or from a periodic checking of things, actually what's going on. Because, you can look at a process, leave, go away, and 3 people will see the same process, but 3 people will have different opinions about what actually happened. It is when you record the stuff you now can have a better, more meaningful conversation. So recording checklists, e.g., has anybody been a lifeguard before? Anyone? No
Just
one?
Baywatch.
Huh?
No.
Just Baywatch.
No.
You watch Baywatch? I don't know if in I don't know if in Baywatch they showed how lifeguards from time to time have to check a pool. This is like at a pool, right? Where the acidity and the chlorine they put in the water, they have to strike the right balance so as to not make people sick, so as to not, cause the pool to deteriorate. So the balance of acidity in the water and the chlorine matters to both human beings' safety and the pool's basic upkeep and to minimize the deterioration of the pool surface. And lifeguards at public pools are required to record ever so often, like several hours, several times in a day, something about the pH balance of the pool and all that. Checklists are things like we used in the military. When we would close up a building, we'd have to go around and we'd have a checklist and we'd have to check off safe number 1 is closed and secure. Safe number 2 is closed and secure. So recording check sheet are recording data as it's necessary going forward. A checklist is simply checking off, much like an airplane pilot does. 2 key tools, measle charts. Measle charts, if you've been to a rent-a-car agency, you'll see here on the right side, the measle chart. That is when you get ready to leave the rent-a-car agency, you make a round, you walk around the car once or twice, and you record by an X any place you feel was damaged already before you left. That's another type of check sheet. Okay, measle charts, inspection checklist, and recording check sheets. So flow charts, we've covered flow charts. So I've taken several of the flow charts out of this presentation because we covered it the last time. But it's important to highlight it's one of the 7 quality tools. It's used for visualizing a process, sequence of events, tasks, activities, steps, whatever terminology you use. And you're using it to identify opportunities for improvement. Remember, I said in the last session, flow charting is for you to put it up on the wall, have everybody step back, and then go, my word, this is a mess. That's the first use of a tool, is to make the process visible. And when you have a very messy, process, lines crisscross and everything is not clean, it becomes very easy to start to pinpoint opportunities for improvement or PIPs. They can be used to identify not only opportunities, but also for streamlining, where you have redundancies way too much. And it can be drawn with standard symbols. Now, I showed last time the symbols that the Lean uses in their methodology. This is a simple flow chart you could use in computer science. I used to do programming a long, long time ago. And, the diamond is a decision-making process. The diagonal looking square thing sort of is really an input or an output. And here's a process step. And the circle sort of takes you someplace else. I got a node here, but on another page, you need to go look at it. So whether you're using Lean, cardinality, or what we call Lean symbols, or whether you're using computer symbols, essentially flow charting is one of the 7 tools often used. There's 5 or 6 different types. Okay, a histogram. Everybody knows what a histogram is, I think, right? I mean, if you remember your introduction to statistics, it's simply a way to classify, in most cases, the attribute data. And for various kinds of data, you would sort of categorically list. And I think we have an illustration on the next slide. And it's really a way to graphically display data. So histogram really is giving you a view, and this is somewhat of a normal distribution. But the histogram is giving you a display of the probable center. When you look at a picture of a histogram, you can identify not only the spread of how many different categories are being looked at, you can also get an idea of the shape of the data being displayed and where maybe the central tendency for that information might be. And here's one that's skewed to the left. and this is a frequency of test score example, right? So you have scores that came here, 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 and you see the number of scores, the mode, which would be those scores that most occurred was right here. So in something like this, the mean would be to the left of the median. So you probably have the mode would be here, the median would probably be somewhere here. Now, I'm not a statistician, but all it matters is to know that, remember, if you're looking at data and you really are just getting a cursory review of it as a consultant, analyst, whatever, you can always bring in an expert to do a deeper dive in some statistics. So we're not going to do a whole lot of that, except to appreciate the fact that on a normal distribution, the mode, the mean, and the median are all the same. But on a skewed distribution, generally, the mode will be always to the right. If it's skewed, this is skewed to the left or skewed negatively, right? The mean will be somewhere over here, like around here, and the mean, that is, and the median would be somewhere in between the mode and the median. The mode and the mean, I'm sorry. So real quick again, the highest number is the mode. The average with a skewed distribution like this is probably over here somewhere, and the median would be to the right of the average. Fair enough? It's just to give us a picture of data. Now, the one thing that that I think is real cool and key, and you'll see it time and time again, whether you use a normal distributions or statistical analysis, everybody's familiar with the 80-20 rule, right? This is reoccurring from time to time. And the guy who really came up with this is very interesting. I made a note for myself to remind myself, is that Wilfredo, I think his name was Wilfredo Pareto, who I think was Italian, but sort of went to French schools or something like that. But in any case, I mean, you can look him up. Here's the big deal with him. He actually was commissioned a couple of different times to look at different data. The first time he looked at things, Wilfredo, he was looking at really what was the empirical observed situation with growing beans. And he noticed that a certain bean he was analyzing, and he was working in the agriculture business at the time doing the analysis, 20% of a particular strain of beans yielded 80% of the crop. He then switched over and did an analysis for the police and realized whole different section of society. And he realized that 80% of the crimes were being done repeatedly by 20% of the criminals that he was analyzing. So that is to say, a lot of people would go to jail, but he noticed that a certain group of criminals really were the folks responsible for 80% of all the crimes. And I think that was for, I want to say, where was it? It's a different part, entirely different country, right? And then that was for, I want to say Milan, police department. And then he did another analysis for land ownership, okay? And looked in a part of European society where he did the analysis of land ownership and realized that 20% of the people owned 80% of the land. So these three different sectors of society, Pareto, came up with his 80-20 rule. And why is that significant for quality? Ideally, when you have limited resources, and this is always the case, and the very next week, I'm going to sort of wrap it up with some sustainability kinds of tools that I'll give you guys. But essentially, you only have a little bit of resource. When someone's paying a lean consultant or an Adizes consultant to come in and help us do things better, I only have $1. I need to know where I'm going to put this resource. And the reason quality analysis and having an idea about how you're going to go about taking your measurements and determining what to go after, here's where a Pareto chart becomes vitally important. Because if you target the proper 20% problem area, you're going to get a yield of 80% of the solutions. You know, you move that targeting apparatus or focus someplace on the wrong part of the problem, you're going to miss it. You're going to be precisely wrong, right?
Daryl, can you repeat that phrase again? If you, what did you say?
I said the Pareto analysis, the 80-20 rule, becomes really important when you're determining where to put your key resources to improve something. And if you just willy-nilly, without any data collected to get an idea of where the big problems are, if you focus your attention on the wrong 20%, then you miss a lot of the goodness, so to speak. You miss capitalizing on the real problems. And let me see, the next slide might help. Hold on. So, for instance, this slide will help a little bit, okay? So this is your typical, if there was nothing we did in statistics, but to just simply plot a Pareto analysis, you're basically looking here at, now notice this cumulative number, okay? You see there, guys? So right here, you come across, now this percent, right? This percent here is giving you against the axis, the axis, this percent is telling you what percent of A is contributing to the cumulative score. So 30% of the problems, let's say, are being caused by A, category A, whatever that is, test scores, whatever it is, or defects, whatever. Let's call them defects, frequency of problems showing up in the process. Then you come up to this next data point. And notice, guys, that these two data points, you come across here, right, where it occurred 90% frequency this thing is happening. And at this point, cumulatively, A and B are contributing to 55% of the problems. You guys see that? Only two categories. Now, one more time, let's go. We go up to category C. The cumulative score of category C we come across. Here you go. This is Pareto, classic Pareto. The first three categories will yield 80% of the problems. So there's really no need for you to look at all these other things. So Pareto helps you to properly prioritize using data to decide where your resource, where you will apply your resource. For instance, you could say, we got problems with process A, B, C, D, E, F, G, but the guy who works in process H and I is the loudest person in the room. They're banging the table all the time. He's very active, his wife is the head of HR, and this person here is going to get the attention. But in fact, these three problems here far outweigh this near 3% problems that just because he's the loudest person in the room doesn't mean he needs to get the attention of the process improvement team, right? Whereas if you put your money on these three, somebody in the decision-making loop is going to see a significant difference. Vice hanging out with the loud table banger whose wife is head of HR. And that's why, data becomes important. It's like, in God we trust, everybody else bring data, right? So this is a really key tool. Pareto was he was a polymath. I mean, he did everything, and when he went into the economic sector for land, he went into the police sector for criminology, and then he studied the yield of beans. He saw this pattern universally, and we fast forward to today, and it's one of the key tools. If there's nothing else, when you Pareto something that you're comparing, you're going to gain some big insights. Okay.
Daryl, can I ask a question at this point? Can you just go back to the last chart?
Hold on. Okay, go ahead, John.
If we think about the SYNDAG process that we then go and plot all of the pips onto the attribution spreadsheet.
Uh-huh.
That's right. It would seem to me that a lot of the how should I put it? It seems that with at least under the Adizes methodology, it's less about which is the thing that's causing the highest amount of stuff. It's more about, approaching things by building mutual trust and respect, starting with small issues, working our way up to the big ones. The big ones we might leave for later because it's mission, structure, information flows, that kind of thing.
Right.
So do you see a conflict between that approach and this approach, which would be, go straight for your big ones, even if the company doesn't have the capability, capacity, mutual trust and respect to actually handle those big ones?
Well, okay, so that's a good question. And so just so you know, Don, I signed up to provide the lean purist point of view, right?
Yeah.
But if permitted to respond to that question, this is how I would answer it, right? In a purely lean way of thinking about it, in any Lean Six Sigma or particularly lean practice, you have two pillars. One pillar is the cultural dynamics in the organization, vis-a-vis change management and the health of the organization. Is there high levels of mutual trust and respect, so on and so forth? So one is smart to have an insight into what that is. So when we're doing the SINDAG and we're looking at the attribution map and seeing where the problems are popping up, that is the holistic point of view. So that's the 50,000 foot. You're looking down and everybody's stepping back, and the view you're taking has more to do with the culture, I would contend, of the organization at that instant. And you put that to the side. That's a pillar, a constant pillar in Lean Six Sigma practices. Put that to the side. The second pillar is really, think of it like this. This is the tools, methods, techniques you will use to address any number of problems. So the problems you see in culture, I would contend, certainly phase 1, 2, and 3 of Adizes addresses completely. And it tends to be focused on culture. Now, once you have affinitized, is my word, or once you have come up with themes for the PIPs that have been categorically placed in one of the attribute map blocks, once you go into that block, that's when you would use a Pareto chart. Okay, we got 16 PIPs in customer interface, or we have 25 PIPs in transformation, or we have 10 PIPs in finance. Then you take that conversation, that dialogue, and you try to apply some of these quality tools. It may not be the Pareto analysis, maybe something else. But does that make sense?
Yeah, no, it makes it makes sense, but it's sort of, I guess it's using both of them correctly, in that even inside, say, transformation PIPs, if you Paretoed at day one, the Pareto analysis may lead you to something that you don't yet have the capability, capacity, mutual trust and respect for, compared to, so anyway,
no, that's a good point.
It would be using,
in that case, and therein lies the conversation. When the Kaizen team is together, we have these 5 things going on. We know that the 2 processes here are really the problem area, but we just don't, that's going to be challenging to pull off. So let's go do something that's a quicker win, and that's okay. But that decision was made consciously. It's not that you were not aware that process A and B are the real beast in the room, but that, you know what? If we go do process I with the loud table banger, whose wife is also the head of HR, they'll feel good, and they will start pounding the table to give us access to those A and B processes. So that becomes like the human dynamic in the game, Yeah. So it's not an either or process. It's really a both and. It's just a timing issue. So it's a good question. Okay.
Thank you.
So scatter diagrams. Scatter diagrams are interesting. They're used to determine whether or not relationships exist between 2 factors. Now, note, it says will not prove that cause and effect relationship exist. Okay, this is a study in 1949. I made a note. A study in 1949 of a scatter diagram, which had always been thought of is plotting A against Y, and some type of causality was inferred. But in fact, there was a study in 1949 of the Journal of American Statistics that correlated the high degree of correlation between potholes in Dublin, Ireland, and diaper rash in the Netherlands, I think it was, and more or less showed a positive relationship between these two. But the fact of the matter is, no common sense person would say to themselves, there's a correlation between diaper rash in Dublin, potholes in Dublin and diaper rash in the Netherlands. And I may have the countries off, but the point is, they're two different countries, two different factors, and they showed some type of correlation. Well, the takeaway from that study, and it's important why I bring it up here, is that a scatter diagram enables you to test your hunches. You may have something there, but not necessarily. Examples, ice cream sales as they relate to the weather. As it gets hotter, outside, the temperature gets hotter, you're probably going to have a demand for more selling more ice cream, Now, so that you can use a scatter diagram essentially, which is here on this slide, number 16. Essentially, this is showing a positive and a tight correlation between factor B and factor A. The main takeaway from scatter diagrams, there may be something there. There may be something there. Without a lot of regression analysis and all the other statistical nice things to do, you don't really know that. You can only test your hunches. So here, this narrow band, there's a direct relationship, when it goes up like that. This is a wide band, and it's a negative relationship. So there's an inverse relationship. So the whole point of it is scatter diagrams can be used to also give you insight and to make a picture of what data is trying to tell you. Control charts. Control charts are used a lot in production, you guys. I brought, I'll send it to you guys. I brought some examples of control charts. Let's see if I have it. All right. So I am going to send you guys, this is a catalog, and the company is called Visual Workspace. So I think this company is the best company that I know of anyway. There may be a counterpart somewhere in other parts of the world, but in the United States, the reason I ordered these, and I'm going to give them to the head office to send to you guys who are in the class. I'm not hawking this woman's products, but the point is this. In her book, she has many tools when you are engaged in a lean operation, a lean process of any kind. Having visuals so that a person can actually know exactly where to go, what to do, including, and the reason I bring it up right now, she has a number of standardized process charts. You just use like a whiteboard, right? She's already pre-printed the things that you would need for a control chart, and you just plot your points daily, hourly, and tools, Visual Workspace, which relates to the 5S. So you have 5S, which we didn't cover. I suggested you guys watch the videos from Boeing. Visual Workspace, I believe, is the secret ingredient of lean. Because when you walk into a building and you know that, I don't see any human beings, but the sign right there says if you're looking for, HR and Daryl Gooden or whatever, to the degree you walk into a building with no human being in it, and the building can inform you, this is a lean, complete operation, and Visual Workspace is important. So I bring it up right now because she has a number of examples of control charts in her catalog, and you have two different kinds of data you would put on a control chart: attribute data, which is the counts, and variable data, like time, the things that happen over time, So, and it's used to determine if variation is inherent in the system. So here's the thing. You could have a process be out of tolerance, but that process, based on the expectation of the customer, is out of tolerance simply because it's just common to how the setup was. So there's two kinds of variation. One is common cause, which means it's baked in the system. We have problems here because that's, it's in our culture, so baked into the system probably lends itself to a lot of cultural, it's the way we get things done around here, those kinds of factors. Or you could, in fact, have a poorly designed process completely across the board. That would be considered common cause variation. All of the stuff is messed up all the damn time. Another kind could be special cause. And it's important because you approach them differently when you're dealing with them. So a control chart that demonstrates special cause variation points out points of out of control limits, increasing, decreasing, something along that lines. To reduce special cause, right, you find the assignable cause, if appropriate, take action to prevent it. And there are things we're going to touch upon at the end of this session today, standard operating procedures. Remember, we did the pig exercise?
Yes.
There was one error in the pig exercise, you guys, I forgot to point out, and I caught it at the end, besides difficulty in maybe doing it virtually. On the very last page where we saw the illustration of the pig, that really was to point out standard work. Now here's the takeaway. Standard operating procedures are good, but they tend to be written by someone, let's just say for talking purposes, not really familiar with doing the work. They are writers. They may be engineers. They may have done the work years ago, and they generally might know something. The difference between standard work and standard operating procedures is that standard work tends to be something written from the perspective of the person doing the work, like in real language. You get certain instructions with equipment. You're like, what the hell is this telling me? This is written by a professional technical writer and not Daryl, who says, you know what, when I walk into a building, I want to see the stuff. And so the common language is important. And I only pointed out because when we did the pig exercise, I realized I didn't highlight the difference between standard operating procedures and standard work. And the difference is standard work is in the common man language. Okay, standard operating procedures tend to be sterile, for lack of a better word. And to the degree you can make your instructions clear to the people doing the work, it's a good thing. So in control processes, if no out of control conditions exist, then the process is said to be in control. All right. In control processes demonstrate these kind of things. There's normal variation, which is systems variation. It's just built into the cake due to the nature of how we set this thing up. You may have laid the plan out in a certain way that what you get is what you get. Had you laid it out differently, you might be able to get 25 more of those items off the line every day. But because of how the plant is laid out, and remember we looked at the spaghetti diagram where folks were running around and equipment was being moved constantly, that layout was a systems problem. To reduce common cause variation, you just have to relay the plant out, buy new equipment, and just basically change the system. It's a systems level problem. So this is a control chart example where the mean there is 14.24. I won't belabor this except to say that this is an example of one. I'm going to touch upon one of the tools I have found always useful. My favorite, actually, of all these tools. This is the one I always found because I found it facilitated dialogue and discussion more than the other tools, in my opinion. The other tools were good for reporting out in front of an executive board or something like that. This tool, the fishbone diagram, which sometimes we call the Ishikawa fishbone diagram, is useful because it helps to make for a conversation. So it allows you to break the problem down in bite-sized pieces, and it gives you more use than the scatter diagram or some of the others for cause and effect. So, and here's how it works. So you have a number of sources that could be considered causes. And the common kinds of things when you do a Ishikawa diagram, purely art, you guys, there's a bit of science to it. But again, you're designing something because you're having a conversation and you're going to say, okay, we have a problem here. Was the nature of this problem caused by man, by methods, machines, materials, measurements, or was it Mother Nature? So there's 1, 2, 3, 4, 5. And this is not by definition. You can make these anything you want based on the nature of the problem you're trying to review. Fair enough? Everybody with me?
It can be the market, anything?
Yes, it could be anything. And this is suggested causes, but that's not cast in stone. This is the general case. Any problem is probably going to have a methods issue causing it, or could. It could have a man-made issue causing it. It could be materials. You just bought bad shit, and therefore, shit in, shit out, right? You could have measurements be all off, or Mother Nature could have caused your problem. So, but yes, Jorge, any problem is easily dealt with the Ishikawa diagram. We did analysis for contracts offices. We did analysis for shipbuilding facilities. The size of the problem or the nature of the problem didn't matter. The game that's being played with this is this. And I may not go through all these slides, but just enough to get you an idea. So we have a problem. Pick one main cause and ask, why did the main cause occur? Result in cause ABC. So work one category at a time. Essentially, so, you saw the previous slide where we decided early on in the session, we got 5 potential causes of this problem. Okay, good. Let's start with the first one. All right. And the way you work the Ishikawa cause and effect diagram is you ask the why. Why did the main cause occur? Whatever this main cause is. It's very abstract here. And I have a example that might bring it home a little bit later for you guys, but this is kind of abstract. Why did the main cause it happened because we didn't have enough people. It happened because Joe Blow quit, thinking that the main cause is people, right? And why? And then once you get that one, you could branch that off and, again, going more than 3 levels deep, like we said last time on the flow diagram, it's not necessary. But here's a key thing. Key thing, which would be on a test if you were taking a green belt test with us, we ask why 5 times. Now, this is a staple concept in lean practices. Basically ask why 5 times. Just remember that. Why did this thing cause the problem? You answer that. And why did that occur? You answer that. So it's 1, 2, 3, 4, 5. Essentially, the point is after about 5 whys, it's like your kid riding in your car with you. Why is the sky blue, Daddy? Well, the sky is blue because it's the atmosphere of the earth. Well, why does the earth have an atmosphere? Well, because, the sun is doing this. So, by the time your kid asks you why the 4th or 5th time, you said, just trust me, right? So it's something like that, right? It's something like that. Not quite like that, but something like that. But the 5 whys inquiry is important because you're looking for root cause here. Root cause is why you go about the task. And see here, you repeat you repeat a series of inquiries, and it is your intuition when you say, aha, this is interesting. No need to go up and down this path anymore because I got a cause in main cause 1 and 3 that I think are repeating now. So here's what goes on. You notice we went through this exercise, and this is zooming through it very abstractly, you guys. We see a root cause A occurring in main cause here, and we see a root cause A occurring in the main cause in a whole separate vein of causes. So cause 4 and 3 both repeated something about Department A giving us faulty parts. Department A gave us faulty parts to get this done. They gave us faulty parts to get that done. We see a pattern here, all right? And so you could have several main causes, okay? Now, to make it a little less abstract, you guys, here's an example of someone being late for class. Who was it? Sridhar, you came late to class, right? You did your push-ups, right?
Yeah.
Why were you late?
Because there was a meeting in my housing colony, which is an annual affair, a legal affair, which I have left and delegated my wife to attend.
Right.
But I had to close the affair. Yeah.
Right. And that was that had something to do with, let's just say, there was a reason. There was a method. There was a meeting. So the method that I'll just play with the thought there. Thank you for indulging us. So, but basically, being late for class that could have been a whole nother vein, is that, we had obligations with the association, put that there. Okay. But if the method for late for class, in the general case, you could say a method was I took the wrong detour, right? Or you could say the machines, right? I was late for class because the alarm clock broke, and or a whole nother cause could be the car broke, right? Well, you look at this, you say, power went off while I was sleeping, thus the alarm clock broke and didn't work, which made me late. Or you could say, in terms of Mother Nature, why were you late for class? Well, it was raining heavy, and there was an accident that closed the tunnel, right? And so on and so forth. The material, well, I had a flat tire. Why was the tire flat? Well, it was defective rubber on the tire, So it's a way, and I really think the Ishikawa diagram lends itself to the kinds of work easily that you guys do with the Adizes methodology.
Where do you stop though, Daryl? Is there you talked about 5 things before, but like in these kinds of things, do you try and differentiate between what you control and what you don't control?
I would say you stop when you start to see a pattern emerge. And this is a very simple example, but let me play with this one. So why was I late for class? Well, you can almost say, a combination. Well, this might be hard to bridge that, but okay. So let me answer it like this, Don.
No, but I'm just saying, like, as an example, flat tire, defective rubber. We have bad rubber plantations, and the Chinese government has stopped good rubber importation or something. Yes. Like, you're getting into some pretty abstract stuff that you just can't do anything about.
Right. You stop when I mention this a bit, Art. You stop when you if you start to see 1 or 2 patterns, or you feel everybody in the room feels, okay, we're saturated here. We think we got this, and 1 or 2 or 3 things may jump out at you. So it's one of the tools to make the information visible. The reason I like the Ishikawa fishbone diagrams is because it's a useful tool for having dialogue. So you're still getting that root cause analysis, not so much in a statistical analysis mindset, but more in a dialogue mindset. There is empirical evidence that we in front of us. We do this, and everyone's doing autobob. Everybody's shaking their head. That's it. That's it. And so you stop when you believe you've come up with reasonable root causes. The game with this is you're trying to find root cause.
I think, if I may, if you look, for example, at the spreadsheet, the PIP allocation spreadsheet,
right.
It's just a different visual representation for something like this. So if you start in column 6, for example, and say, okay, we're starting to lose customers, right?
Right.
So that's 6P ineffectiveness. Why? Well, because our client interface of system is not working properly.
Right.
Okay, why? Well, because our information flow is not, getting the information out there. Why? Because we're not structured correctly. Why? Because we don't have a culture of mutual trust and respect.
Right.
So if I think that there's a lot of value here. I think probably the only difference is against the fishbone. We need to look at for example, from the spreadsheet perspective, it's going to be more of a cycle, not a straight line, which is something we always tell our clients. It's not, from start to end, but then it starts all over again. So it's cyclic.
Right.
And so I think there could be a good possibility to probably redesign the way we visually present the spreadsheet, maybe through a circular fishbone that could make it easier to explain to some people, particularly during the scene where this is the main tool. So I think there's a lot of value there. And then also, if you look at, I don't know, for example, senior teams, when you're doing the diagnosis part of a senior team, you start collecting pips, then you pattern them. So instead of using the classic, spreadsheet, Excel spreadsheet tool, I think using this fishbone tool could be a better idea.
It could be, and it's a nod towards the mixed method, saying, it's just one of the tools. It definitely could be. You could take, yes. I completely can see that being a good approach for that. Absolutely. And No, it's good, Alvaro. Yeah. So here is one that this is particularly useful in engineering, in the engineering field, you guys. So this may be a bit too esoteric, but it's important to add it here. Failure modes and effect analysis. Now, I used to do something called failure modes and criticality analysis, all the same thing. Essentially, it's a risk assessment method for identifying and analyzing, as well as prioritizing and documenting potential failures that could occur. And this has good relevance to products, really good relevance to people putting products out the door. And it's a living document, kind of a run sheet. And again, you're going to get some of those basic, already printed tools like this. You walk in with your portfolio. Oh, yeah, I'm from Adizes, and oh, yeah, we have a mixed methodology where we maximize and optimize how you use lean in an organization. So you come in with ready-made cards, and it's voila. So it answers these questions. Familiar answers these questions. What the customer will experience if a key process input fails, okay? So the customer's expecting to get something, but this thing can fail any number of ways. Do you know how many different ways this thing can fail? Without a failure modes and effect analysis, you're speculating and bullshitting. But this actually makes it explicit and points out connection points of why the probability of that failure is critical to your end result, and how to prevent it is the idea behind it. So in what action, when I said to prevent it, what action is needed to be taken to minimize the potential risk of this thing? So this is more of an anticipatory, you're anticipating now with a familiar, you're playing the game of, I'm so good at this stuff. I'm going to give you a chart in which we're going to discuss the potential failures that could be experienced. And here's the deal. To the degree you have the time, you're going to consider all the modes in which a system or process could fail. Now, this may be a luxury, but see, when you're putting missiles on board a ship, it's not a luxury. It's a requirement, because you have potential for people dying, as is the case, with chemicals. I mean, if you're a manufacturer of pharmaceuticals and you get the mixture wrong in something or another, you're playing around with people's lives. So in a lot of industries, chemical intensive industries, biomedicine, weapons, things where things go boom, or shit can really go bad fast for a lot of people, familiar becomes real important. And so there's 3 points: the criticality, to help you prioritize the failure modes. How critical, if something happens, is this to the process? How frequently is this thing happening? And the ability to escape detection. So if a particular mode of failure can escape detection, it's a problem. And this is a product. Risk priority number is a product of the criticality, the frequency, and the detection, the ability to hide detection, right? And for the sake of going forward, I want to touch upon some of the other slides and give you guys a 5-minute break. Here's what's useful. You notice on this slide, it says, door. Okay, so here, this is a failure modes and effect analysis of building elevators, okay, of the building elevators. So failure mode, one thing could happen, the misalignment of the plastic gib could occur. The failure effect, right, the failure mode is that, the failure effect is the door will not close. Is this a problem on a scale of 1 to 10, 10 being the highest? Severity is a big issue here, and I probably went too fast over severity. So severity scale, no effect. 2, minor loss of performance. 3, minor loss of performance. So the first one is minor loss of performance, negligible effect. Second one is minor loss of performance, then reduced performance. And 4, minor inability to meet customer requirements. 5 starts being a flashing yellow light, right? 6, inability to meet customer requirements. Now it's a flashing red light. Cause serious customer dissatisfaction. Now they start pulling their contracts from you. Cause a failure, break regulatory or other laws. And 10 is we're hurting people now. Okay, so those severity numbers go from 1 to 10, 10 being the highest, that means it's a serious failure mode. Okay, the cause, pushing or hitting door transversely, whatever that word means. I'm not sure what transversely means, but essentially we're pushing this door in some strange way. How often does it occur? It occurs enough. It's past the midpoint of occurrence. And is it proper use of elevators detect? So people may not have a way of detecting, and when it's a 5, it's in the middle of the road. So here's the thing. You come across here, and this RPN, which is the product of the criticality, the frequency, and the ability to escape detection, right? 10 always being the highest. So 300. So if you look at this, guys, and I went through that fast. Let me just ask a question, see if everybody's still awake. You still there, Don? Did he sign off?
Oh, yeah.
No, I'm here, Daryl.
Oh, bless your heart, man. All right.
I'm not going anywhere.
I know. I mean, it's late, man. I can understand it. But anyway, we are recording. So you look at the score here to the right, right? And remember, if the score is a product of the risk priority number, it's the frequency, the criticality, and the ability to hide. Which of these failure modes would you say, if you look at the right column, would you say is the one that we should attack first? Anybody?
Repeat the question again.
When you look at the score, the RPN score, which is the risk analysis for dealing with the severity, the occurrence, and the ability to hide detection, 10 always being the highest, the product of that score gives you the highest probability of this thing failing.
Micro scan failure.
Yeah. Right. The microscan failure would be the highest because it has the highest risk number. All this is putting into categories the same component. This building elevator has a number of ways in which it could fail. However, if the microscan fails, door will not close, dirty cover, it will not close, proper housekeeping. Basically, they're saying this one here has got an 8, a 9, and a 10. Of all the failure modes, this one is the most problem. Now, as an example, the takeaway from the familia is simply you write down, you do an analysis of, is it really critical? Does it hurt people? So on and so forth. And it may not be as clear to you guys. I don't really know building elevator technology, but back to the importance of the people who do the work. They will know when something is bad and the cost to the business, the cost to their department or to the client, they are the ones who come up with these numbers. These are not like, these are best judgment kinds of calls. And so you're going to build an empirical observation of what things are. And then you get the people who do the work and they can have a more intelligent conversation. We're not building elevator experts, and you guys are maybe seeing failure modes and effect analysis for the first time. And with that, that was real fast to go through some of the tools. We're gonna pause here for 5 minutes, take a 5-minute break, you guys, and then I'll be back, and then we'll open up any questions you guys may have, because I'm doing a lot of talking, a lot of transmitting. So I'd like to, when we get back, any thoughts, comments you have about anything from the previous 2 sessions and today, and then we'll go on.
Okay.
All right.
Okay.
Yeah.
How are my Mexican friends traveling down there with all the earthquakes?
Yeah, it's pretty tough.
There was another one this morning.
Well, when I had my insurance claims business, I spent about 3 years in Christchurch after that earthquake, and the aftershocks take a little while to get used to, I must admit.
Yeah. But there was also an earthquake in California, was it, Daryl? Oh, he left. But there was a tremor outside California, right?
Okay,
You're muted. You're
Yeah,
muted.
I was muted. I don't know. I haven't heard about that, but probably. I mean, I wouldn't be surprised. I just
Yeah, I saw it in CNN yesterday.
is that right? Yeah. So I haven't watched the news in about.
Fake news. Fake news.
It was
Fake news.
CNM. CNN.
I'm up in the Bay Area right now, and I haven't watched the news in the last days. Usually, I watch 2 hours of news, but I
Okay.
didn't hear about that though. So, anyway, I thought about that, man. You know, it's like hurricanes, earthquakes. It's like the end of the world type scenarios, you know. So,
Yeah.
you know,
Yeah.
Nature can tolerate only so much. Huh? Nature is after us.
You think nature's after us?
No, we are after nature. So
Yeah.
how can it tolerate?
No, I know. I heard about a machine that someone has that's a weather machine. You know, somebody was telling me, you know, it's a secret weapon that someone has, like, you know, conspiracy theories, but, you know, I don't know.
Yeah, it has a weird name. I've heard of it too. Yeah.
Okay, yeah. This woman wrote a whole book on it. I'm like, oh, interesting. Yeah. Why would anybody turn?
Has the earthquake managed to contaminate the water over there, and it's affecting you?
I don't think so.
All of these people, I think we have Guadalajara and Monterrey, isn't it?
Well, they had a few. Well, there was a few people in Mexico City too, right?
I was there actually.
Were you?
Jaime Batis was there too.
Huh.
I spoke to Humberto.
We're here.
Hey, you know, the last time I watched it, they were trying desperately to get some kids out of a school. Did anything?
Yeah.
What happened?
21 died and 5 adults.
What?
21 kids and 5 adults died in that kinder.
Man, yeah, that's tragic. Yeah.
Yeah. There are over 250 deaths now, and I believe 38 buildings came down.
Wow. Yeah, earthquakes, yeah. I don't know where you could live. I mean, I don't know where you could live to avoid either Mother Nature, you know, or something.
Well, if you come to Australia, we don't have the earthquakes. We just have every animal on the planet that will kill you, from spiders to snakes to octopuses. So it depends what you feel like.
Yeah.
But you'll all be, remember February 2019, I expect to see everybody down here. I will be making a safe environment.
No critters.
Well, if you misbehave, if you turn up late to the meeting, push-ups don't save you. Where I come from, you're in with the snakes, you're in with the spiders.
Then I'm not going to be able to go, Don.
Oh, you're definitely going to have to. Well, as you saw from where Shoham picked up the snake at my place, there was only a little one. It was about 1 meter. I found a snake skin from one that was about 3 meters. So there's a big boy hanging around there somewhere. Oh, just a carpet snake. It's fine. All good.
Is that 5 minutes? Let me see. I'm always figuring this out. Why is that doing?
You're doing very well, Daryl.
You guys see that? You guys see?
Yeah.
Okay. And I'm off of mute now? Okay. All right. Is everybody back?
Yes, we are.
All right.
We're here.
All right. So when we first talked about this, you know, we were thinking about going to Guadalajara. So I'm glad we ended up opening it up to a lot more folks. But one of the things I always wanted to make sure we got was Six Sigma, recall, was really, it came about a whole lot from the manufacturing side of things. GE and 3M were the big proponents of Six Sigma quality, okay? And, you know, you have these camps, just so you guys know, just background. I like to talk about this, but and then I'll open it up if any questions anybody has. You have these camps. You have people who really believe in the purity of Six Sigma. And as far as they're concerned, if you don't have data analysis and depth of insight and understanding of statistical process controls, yeah, you know, you're just, you know, social scientists playing around with people, you know, no real data. The lean people are much closer. The lean purists have much more in common with Adizes practitioners by nature. By definition, it just lends itself there a lot more. Okay, so the point I'm making is that to the degree you can season your methods and your approach to things with some of the Six Sigma quality kinds of ideas, I believe it gives you an additional, just something else that's a little bit better. Not better is not the right word. It gives you another level of confidence. I put it like that. When you can quantify something, not in some overly rigorous manner, but when you can speak to data that's useful and relevant, it helps to make your arguments stronger, in my opinion. Now, there could be people in the room, no matter what data you bring them, they're not going to give you the light of day, and they're going to have a problem no matter what. Nevertheless, it is a useful tool to have in your tool bag. And I'll point out again, the define, measure, analyze, improve, and control, that little icon there, that concept is a Six Sigma concept, okay? And we sort of categorically dealt with it as a overview thing. But define, measure, analyze, improve, control, straight out of Six Sigma, okay? Just so you know what you're looking at. DMAIC, they call it DMAIC. So I put these two sessions together mainly because one, I thought was more useful to focus on how to do the analysis. And now we delve into a little bit more of how we improve. So at the end of this lesson, you'll be able to describe measurement systems and identify measurement methods for continuous and discrete data. Useful, particularly for things like FAMIA and any other thing you were having to record numbers and take data information out on, right? Even if it's nothing more than to talk to manufacturing engineers, to stay with them and what they're talking about, okay? Because they will talk in this language. Determine the measurement system capability. So process capability is a big idea, you know, and we're probably going to touch upon that in the next session, process capability. Identify and explain the objectives and benefits of statistical process control. This is the object of this next few sessions. These next few slides. And this whole concept of applying mistake proofing, which is another big concept of lean. So they have all these big concepts. That's a lean concept. But here's the thing. One area I think it's useful to revisit. You saw this in the very first day, the very first session. Why Six Sigma? And so this is repeating, but you know, you repeat it. We've covered a lot of material, so a few of these slides I put back in just so the point is made. 99% is good enough, right? Well, 99% allows you to have 20,000 lost postal mail items per hour, 50 minutes of unsafe drinking water every day, 2 long or short landings per day at a major airport, 5,000 incorrect surgical operations per week, 7 hours of electrical hours lost per month, and 20,000 prescriptions, incorrect prescriptions per month. If you go to a Six Sigma quality, Six Sigma is a benchmark. I mean, I may have gone through that real fast, but Six Sigma is meant to be a benchmark. I think it was on the previous slide. Let me see. No, it wasn't. I'm sorry. But it's a benchmark. Okay. And it's a benchmark for perfection. So when you talk of Six Sigma, you're really saying, I'm after perfection here. Now, people talk about zero defects and all these other things. Six Sigma, when you begin to really approach Six Sigma, that 99% moves from 20,000 lost postal mail items to 7 lost postal mail items. But let's drop down to where you have 5,000 incorrect surgical operations, which is just a number if it's not your mother they're operating on. But if they're operating on your mom, or your child, you want 99.99999. The hell with the whoop-de-doo. I want the best, period. And people stop laughing, right? Because when it comes to just a number is a number is a number, but when it's affecting you or your customer, it's different importance. So from 5,000 incorrect surgical operations per week to 1.7 incorrect surgical operations per week is a big difference. Thus, not every industry needs Six Sigma quality. There is a point of diminishing returns, but it's useful to know what that point of diminishing returns is. You can have Six Sigma quality, but the story goes, you may not be able to afford that. But isn't it good that you have an insight and understanding as to what kinds of quality ought your manufacturing plant be yielding, right? It's a useful conversation and understanding to have. So now here's the slide I was looking for. It says here. So Six Sigma as a metric, it's a benchmark for perfection. I said that earlier. And here's the actual number comes out to be this. The Six Sigma process results in only 3.4 defects per million opportunities for that defect to occur. There's 1 million times, out of 1 million times, when you're approaching Six Sigma quality, 3.4 defects will occur for every opportunity the thing could have gone sideways. That's tight. That's a tight spec. Very tight. Not many industries can claim they need Six Sigma quality. Certainly if you're going to the moon, you probably need it. Certainly if you're dealing with some serious life or death situation, you want it. It is a way to measure and monitor variation in a process. And it helps you to drive continuous improvement. And it's useful, as I say, to me, I say it's useful because having an understanding of Six Sigma quality allows you deeper insights into, you could say to someone, well, do you really need it that good? Do you know what extra dollars is going to cost you to get you to that level of perfection? That's what you want. All right. Those conversations can happen because you have an understanding of Six Sigma quality. So all work so here's the basic thinking. I mentioned earlier, in God we trust, everyone else bring data. The Six Sigma people in the world all want data. They're data lovers. I'm not such a big fan of data. I think people can lie about data and all that. But again, I think it's useful for having a conversation. Now on this slide, the lower specification limit and the upper specification limit are defined by the customer. And I did mention before we got started, did you guys have any questions, any thoughts on anything? We go around once. I always like to do a half process check-in because I know I've been talking a lot. Anything, guys?
No, go ahead.
We're fine. Thank you.
Okay. So this is the statistical tools in the tool bag. All right. Not my strongest suit, but I have an appreciation of it because I've seen when I bring one of the real experts in the room, when we have a really sticky problem, they can help me out quite a bit, documenting things and making a case for data. The business improves when they reduce or eliminate variation. That's the big takeaway for Six Sigma. I mentioned this in the previous set of slides, common cause. Common cause variation is inherent in the process. It exhibits only common causes. When a process exhibits only common causes, it's said to be stable. It is what it is. It's a stable process. And stable processes are predictable. Now, if that predictability is not meeting customer needs, then you need to look at the total system and say, okay, we need to rethink the whole process, okay? Because it's not meeting customer expectation. Customers are leaving in droves. back up, regroup, redesign the whole process. Special cause is an assignable variation. It's something unusual, uncommon occurred that knocked this thing out of whack. And a process that exhibits special cause variation is, by definition, an unstable process. And unstable processes are unpredictable. So, you know, when you get a PIP, it wasn't expected or wanted, this is a special cause issue, right? So you are comparing a variations types, right?
Daryl, sorry, I have a question.
Uh-huh.
The last session you talked about the talk approach to prioritize problems.
Mm-hmm.
Remember?
Yeah.
But how does Lean do that?
So, okay. So when in the session when I brought up the theory of constraints, which we were going to talk about next time. So let me see if I understand the question right. So we talked about how to prioritize problems with theory of constraint. Actually, it wasn't so much prioritize problems with theory of constraint. I think the words I used was to focus on problems, which I guess is a way of prioritizing. I guess this lends itself in many ways to the same kind of a thing. For instance, theory of constraint is seen as when you have a common cause. Let me answer it like this. When we are having and dealing with common cause issues, remember common cause is in the system. So theory of constraint takes a systems point of view. Something is wrong in the production of this plant. Find me the bottleneck and address that bottleneck. That is, while I use the term focus, that in essence is one and the same as a priority. We must fix this bottleneck first. And then because it's a systems approach, the thought is with theory of constraints, something else is going to pop up over there now. We address this one, now it's popping up over there. So I would answer it by saying theory of constraint deals with common cause issues. And Six Sigma will sort of take common cause and put it to the side a little bit and put its energies, focus, and attention on special cause. So it's a great question, made me think. Six Sigma lends itself, in my opinion, better to special cause variation. And theory constraint is a much heavier, useful tool when you have system problems, common cause issues. You have a bad plant. Your production facility is woefully lacking in terms of how all our other production factories are producing. Why are you guys so bad? Something's wrong with this whole entire factory. That's a common cause at that one facility. Did that help?
Yeah, it did. So I guess Lean is more focused on the transformation subsystem, right?
I believe so. I mean, I want to just interject. Yeah, I think the entire Lean thing, as I'm viewing it, is going into deep into transformation, touching a little bit on client interface, but it does not probably just go into how to define CAPI. It doesn't have to go into the column 1, 1, 2 at all. It's a lot of process. Yeah. I mean, that's what I perceive. Correct me if I'm wrong.
In principle, I would agree with that statement, Sridhar. I would agree with that, with the one caveat that it lends itself also to other 4 or 5 kinds of sub-processes. That makes sense? But for the most part, I agree with that. Yeah. Okay. Now, I mean, you'll get some purists out there who would disagree with that, but I happen to agree with that.
But they would be wrong.
Yeah. Okay, I agree with you. In principle, I think you're right. Common cause variation overview. So we mentioned earlier, we think the theory of constraint, or at least I thought theory of constraint lends itself to common cause variation more so than anything else. And that said, I won't read the slide to you. The main takeaway, the root causes are in the key elements of the system. And like with theory of constraint, we're looking at the system. The problem is over there. Slight variation in raw materials, slight machine vibrations. How slight, I don't know. But my point on this is you have a problem in the whole system. You're going to use tools, whether it's theory constraint, lean, or anything else, to try to get at that from a systems point of view. Special cause, on the other hand, is caused by some special abnormal activities resulting in an unexpected change in the process output, right? And in this case, you have defective materials, people are untrained, there's programming errors, so you have something making the situation a lot worse because of this particular peculiar issues, not necessarily a systemic issue. And you reduce variation. Two types of variation requires the different approaches. I said, just in conversation today, that elimination, the special cause is isolating the root cause and controlling the process. Reducing common cause, improve the system, vis-a-vis theory constraint, something else. How you anticipate the variation, this whole idea of designing robust processes and products, that goes to the familia. If you're analyzing stuff and you have a failure modes, effect, and analysis, you can do in some type of anticipation about variation. The familia lends itself to that. Reducing common cause, theory constraint lends itself to that. Eliminating special cause, I believe, is the sweet spot of Six Sigma. So I'm going to go over a few process control charts. We covered it a little bit last time. So these are very similar, but the idea is that now we've done some analysis. Now we're trying to tighten up the process in the improved phase here, okay? So statistical process control is the use of these various statistical methods we've talked about to actually begin to bring a process within control. Now, the takeaway from this normal distribution curve is that this 3 sigma, not 6 sigma, you got 3 sigma, you're going to have 97%, if not more. You're going to be pretty much all potential failures can be dealt with in a 3 sigma process, right? I mean, that's the normal distribution. So what are the 3 characteristics of a data set, right? I mentioned it earlier when we talked on the previous presentation about the skew distribution. I talked about the mean, the median, and the mode. And just from your years ago, maybe you don't remember it, but the mean is the average, the median is the most occurring, and the mode is where it's most dominant, right? The spread, which is the width of that normal distribution curve, is where you find the variance, the range, and the percent of variation, okay? And the shape, whether skewed negative with the left tail being long or skewed positive with the right tail being long, or kurtosis is the technical name for that. And how much data is covered by the following in a normal distribution. So 1 standard deviation from the mean in a normal distribution. In a normal distribution, the mode, the mean, and the median are all the same in a normal distribution. 1 standard deviation from that, it's 68% of everything in that population is dealt with within 1 standard deviation. Simply going 2 standard deviations, you have 95% of all possible cases in that population or in that sample are dealt with when you look at standard deviation from the average. And 99.7% of all possible perturbations, challenges, problems, defects will fall within 3 standard deviations. So you can see how when people talk about 6 sigma, you really need to think and know, do you really want 6 sigma? It is not after that 3 standard deviations, you really need to know, are you willing to pay the cost for that kind of quality? And that's really a conversation that's useful. We did something in our analysis we called the readiness analysis, which was to say the uptime of a system on board a ship needed to be potentially up and ready. And by the way, networks now deal with this. Networks are approaching 6 sigma quality. Networks are up almost all of the time. 99.999% of the time, people expect networks to be up. So So it's in the real world showing up in a real sense. But we decided equipment needed to be up 98% of the time. Well, if some admiral said, no, that's not good enough, we could calculate for them, okay, if you want us to buy additional spares, if you want us to buy additional equipment so that the uptime of this equipment is 99.9999, there's going to be another $45 million. You want to pay that? That becomes the conversation, you know? And it may not be big numbers like that for the company you might be dealing with, but quality cost is the thing. Now, you could build it in and make it not so costly. Again, that's a different conversation. I'm trying to move your pictures around so I can see this. All right. So here are another guy, another expert in statistical analysis with Sure. And this is his control charts. A run chart is nothing more than being placed in a, you think about this normal distribution, turn it sideways, you turn it sideways like that, and you can see how you could design a control chart with a basic run chart. So remember now, we went back here and said, you know what, if we got 99.7% of the issues are going to come up with a standard deviation of 3, right? And we're not even talking about Six Sigma quality. We're just saying 99.7% of the time, you can fall within the specs of this upper control limit, lower control limit, which are defined by the customer, right? The customer says it needs to be up and on, 100% of the time. At 5% of the time, I'm struggling to find an example of a customer expectation, but it ought to be clear as to what a customer's tolerance for failure are in terms of a product or service and the range in which you need to be. So why is that important? That's important for the following reasons. All right, control charts are simply run charts bounded by statistical generated limits.
So Daryl, can I just ask a question on that? So isn't it also part of the conversation about like I want 100% uptime when I'm using the system, but when I'm asleep, I don't care if the system goes down. Now the problem is it's probably difficult to forecast when you're going to have your failure, but isn't the conversation about whether you want 3 all the way through to Six Sigma based on the likelihood of when the failure is to occur?
Yes. I mean, there's all kinds of, yes. I mean, in the design of the system, it's presumed when it's not radiating or not on, that it goes into sleep mode. Getting up from the sleep mode to all up mode is a function of the redundancies and the technology built into the system to get it from 0 to there as fast as possible. Now, whatever the technology is that you need to get there, be it electrical, mechanical, be it plasma, whatever the deal is that you're using to get from here to there, you're probably saving some, let's just say you're conserving some energy, you're probably conserving some other resources by not having the system on when it doesn't have to be on. The challenge becomes down when and how fast and how long does it take that system to go from 0 to here? And there are trade-offs. I can wait 2 minutes or whatever. So the short answer is you must take into consideration the nature of the system and the uptime and things like that.
Okay.
I mean, that's how we dealt with radars because they were not always on. But when we wanted them on, we wanted them on. So, and you pay a price for being too slow to come on. So think about when I mentioned the normal curve turning it sideways. That's what's going on, imposing the parameters on a simple run chart with these statistical indicators. So here's the idea with this chart. And out of control conditions are frequently detected by extreme points. So you see here the upper control limit. They circle this point. Why? Because this point has exceeded the upper control limit. This point has exceeded the lower control limit. And you only have this visibility if somebody's actually doing a run chart, testing it every now and then, something like that. A lot of the times this is done in manufacturing. 2 out of 3 points in a zone A or B or beyond. So C is good. I'm well within the limits. I'm bouncing around the average here, right? Now I do some things here. And now what I have here is going on is I have 1, 2, 3, 4, 4 data points falling into, at least 2 data points, 2 out of 3 data points. So out of these 3, 2 of these are in the upper limit. This is a different example. Out of this one, 2 of 3 points are in this risky range, okay? Note that the out of control points is always circled, right? So all the way out. This one, at this point, this is all the way out. It hit there, had it bounced back up there, it'd have been all right. But the fact that 2 of those occurred out of 3 times gives you cause to pause. You guys with me? See that?
Yep, got it.
Yeah. 4 out of 5 points in zone B or beyond. Now, these are indicators of I got a problem. So 4 out of the 5 points in zone B or beyond. So we have 1, 2, 3, 4, with this one being the outermost. So 4 points out of the 5 have fallen to the B zone. I have a trend building here. Something's wrong. The thing has not bounced back and forth in some regular manner about the mean. It's drifting. Why is this thing drifting? Okay. This is the usefulness of a control chart. So this one has 1, 2, 3, 4, and then it went somewhere else here. So this pattern is suspicious also. And, this is simply this is giving you data saying, these are rules of thumb. When you if you didn't have anything else about Six Sigma, but except to be armed with the fact that in a control chart, when I see something is off the chart, I'm going to ask a question, right? When I know that 2 out of 3 data points are falling into the risky zone about to go out of bounds, I'm going to ask a question. If I know how to look at a control chart. And then when I look at a control chart and I see a trend of 7 data points in a row steadily increasing or decreasing, this is a solid trend. Something is wrong. Something is going on, and it's about to go out of bounds. Okay, and so you see here, process shifts 7 points in a row on one side of the center line. Why is this thing locally just doing this? These are when looking at a run chart, you can infer a problem based on the patterns you're recognizing. Oscillation, when you have 14 data points, that's simply a back and forth in some wild manner about the mean. This oscillation, there's something triggering why, it's particularly electronics. You would know that something's going on here. Let's look into this. And therefore, you would take your theory constraint or your Six Sigma practitioner and go and ask why 5 times, right? So root cause. Why find the root cause of a defect? Whether you're using a run chart, using Ishikawa fishbone diagram, scatter diagrams, the Pareto analysis, you're always looking for the root cause of a situation or problem, be it product or process. And the reason you're trying to find it is so that you could take corrective actions and ensure that you put your resources on the right point. And ideally, what you want to do is get to a point where you can prevent defects from being in the loop at all. Okay, root cause analysis. I mean, it's your common sense thing of there is a time, a logical flow that this caused that, and in the attribute map, we had the chain of causality. It's the same kind of thinking in terms of logic. So cause and effect may be separated by time, logic, or location, right? It's a relationship thing. And then it's good to point out that you can have a number of causes affecting the situation, which you could see why a Ishikawa fishbone diagram would be useful in this. And you could have one cause actually, putting into place several different effects. Okay. We touched upon all these tools thus far: the Ishikawa diagram, the Pareto chart for frequency, the scatter diagram. And you take a scatter diagram and you draw a line, you then really have a run chart, you know, and you take a statistical upper and lower bound on a run chart, and now you're bringing into control the ability to understand and how to improve something based on the patterns you see evolve. Any questions, guys? All right.
No,
Just
makes
remind me
sense.
of my MBA.
Would you say, Sridhar? Say it again.
I'm saying it just reminds me of my MBA. Though I did finance, I did operations management too. And,
Oh, yeah.
reminds me a lot. You know, I think there's a lot more structure to it now, I guess.
Yes. No, it's a good point. So we've touched upon 5 whys. I won't give you the lecture again on 5 whys, but you could use the 5 whys in either the run chart or any of those tools. It's not just the Ishikawa diagram. 5 whys is a staple. And, you know, I always say, well, if I'm stuck and I really don't know what the hell this maintenance engineer or this production engineer is telling me, you can always default to, while you're thinking of a good question, to asking why, and make sure you keep account of, have you asked it 5 times? I mean, it's a good, legitimate method to getting that stuff. So I'm going to take you through this. Excuse me for reading it, you guys, but I don't remember the story all the way. So I'm going to read this, okay? And this is a root cause analysis kind of a illustration. So the U.S. Standard Railroad gauge. You guys know about this problem before I go into this? The way you guys knew about the gorilla thing. You know about this standard gauge issue?
Nope.
Yeah.
All right. So if you know, just stay with this, you know, stay with it. And it makes the point of root cause analysis, okay? The U.S. Standard Railroad gauge is 4 feet, 8.5 inches. And that's an exceedingly odd number. Why was the gauge used? Well, it was built that way in England, and the English expatriates came and built the railroads in the United States. Because the first rail lines were built by the same people that built the pre-railroad tramways, and that was essentially, sorry about that, that was essentially why they did it, because the people who built those used the same jigs, tools that they used for building wagons, which used that wheel spacing. Okay, so that gauge for the train came from the wagons that were being built. Okay, why did the wagons use the odd wheel spacing? Well, if they tried to use any other spacing, the wagons would break down, or on some of the old long distance roads, because that spacing of the old wheel ruts were existing. So who built these old roads? And they determined pretty much it was built by the Roman legions. Road have used it ever since the Romans built it, and over time these ruts were grooved into the roads. The initial ruts, which everyone else had to match for fear of destroying their wagons, were first made by the Romans for their chariots. Okay, and then the story goes, thus we have the answer to the original question. That was 5 whys, in case you guys didn't hear them. The United States Standard Railroad gauge, 4 feet, 8.5 inches, derived from the original specifications of an Imperial Roman Army war chariot. Specs and bureaucracies live forever. So the next time you handle aspects of wondering what horse's ass came up with it, you may be exactly right. Why? Because Imperial Roman chariots were made to be just wide enough to accommodate the back end of 2 war horses. And that's why the gauge we use to this day with the railroads is that way. I just thought it was fascinating. Here's a picture of that, right?
And interestingly, with our Argentinian office, when I was listening to a Phase 5 colloquia the other day, somehow the Argentinians have managed to get themselves 2 slightly different track widths, so they can't share machinery between the 2. So yeah, they've made it even more complex.
Wow, yeah, they could use some specification tightening.
Yeah.
Another example was to make this 5 why thing, drilling it home, root cause analysis. The 5 whys relate to root cause analysis. Granite on the Jefferson Memorial is deteriorating. Okay, why? Because they use harsh chemicals. It's eating away the stuff. Why are they using harsh chemicals? To clean pigeon droppings. Okay. Why are the pigeons, why is there so much pigeon dropping? Because there's pigeons, and the pigeons are eating, spiders that live in the monument and provides them good food. So why is it that there's so many spiders? Well, there's so many spiders because spiders eat gnats and they can catch them in their net, and thus that's what they do. So gnats, why are there so many gnats? Gnats are attracted to the light at dusk. They come around right at dusk when the lights are turned on. Solution: turn on the lights at a later time, and you'll get fewer gnats, which means you'll get fewer spiders, which means you'll have fewer pigeons, which means you can wash the granite a little less frequently. Or you could just try to find a whole nother solution to wash it, right? Some newfangled innovation. So we did this one already. The last few things I wanted to touch upon was something known as poka yoki, okay? And it's a Japanese term, which means this is tied in some ways to FAMIA, failure modes effect analysis, okay? It means mistake proofing. If you have a good design, be it a process or product, to the degree you can make sure that the thing is designed so it's not to cause a mistake or defect, that's a better design. Would you agree? Right?
Yeah.
So the first opportunity that Shingo, which by the way, the Lean Award in the United States is named after this guy. So this is the guy who the United States Lean Institute for Lean give the awards, and we won this award. First time for any Navy organization, we won this award, the Shingo Award. The Shingo Award is named after Shigeo Shingo, and the University of Utah is connected to it. But that's the name of our Lean Award for Lean Operation in the United States after him. So Shingo suggested a solution that became the first Poka-yoke device. In the old method, a worker began by taking two springs out of a large box of springs and then assembling a switch of some kind. The problem was that sometimes the worker failed to put both springs in the switch. And this is back in the days, even in the United States, there was in the 60s and 70s, made in Japan was a joke, in all honesty, but people like Shingo, and particularly the guy who I mentioned at the beginning of the whole lecture this time, which Hishikawa, these people were the people instrumental in turning around so that by the 80s, everybody were envious of Japanese quality. It was Shingo and Hishikawa. They were the two heavyweights that really were credited with making Japanese quality the envy of the world. Such that the award for lean operation in the United States is named after Shingo. So his very first project was dealing with these springs and why so many defects were a result of people not putting the springs in. He had a very simple and elegant solution was what he did, very common sense. In the new approach, a small plate simply placed in front of the parts box, and the worker's first task was to take two springs out of the box, put them in the plate. Then the worker assembled the switch. If any springs remained on the plate, he or she knew that he had forgotten to insert springs in the assembly. And it completely eliminated the problem of the missing spring. And he realized he was onto something then and just sort of designed a methodology around that. And it's not really heavy. It's not really rigorous. It's not any of that. It's really common sense. So here's one example. Before, gas caps, people would lose gas caps all the time, and they'd drive away, forget them on top of the gas pump or whatever, using the old style cap. Fast forward to the present, for the last decade or so, they've attached a cord to prevent the caps from being lost. It started with the Japanese cars. And then additionally, the ratchet limits the torque used to tighten up the cap. They designed cones to guide the nozzle inserts so you can't put the wrong kind of gas if you're using diesel, so on and so forth. And then they also included a drain prevention thing that helped paint not be impacted by gas leaking out of the gas cap thing. So this is an example of mistake proofing. Okay, quality. And they're even gone to the point where some gas pumps now are equipped with hose coupling that break away and then quickly shut off the flow of gas. In the 50s and 60s, this was a serious problem, I guess, and it's no longer that way. Now, this is an interesting story. This is a picture of a U-Haul truck. Now, you see the U-Haul truck, you can slide out that ramp. You see that? Right here's a ramp. You can slide this ramp out, and this ramp is used to walk up into the truck and stuff. Well, before they made an automatic locking mechanism, they had a serious accident in San Francisco. A truck was going up the hill. This ramp flew out of its holding there and decapitated the driver driving behind the truck. That driver careened out of control, having been decapitated, and ran onto the sidewalk and killed three children. It was a big suit. But what they did to keep that from ever happening again was they made this automatic locking thing. And every U-Haul truck now has that. It's probably some of their competitors. So mistake proofing is one key component when you're trying to make sure quality is built in. Because the whole idea with quality is build it in. Don't come after the fact and give me a quality assurance plan and all of that. Every person in the process ought to be mindful of how to build quality in the process. I think these are the benefits and results of mistake proofing. We got about 5 more minutes. The next few slides is really arguing for the cost effectiveness of building in mistake proofing. I mean, you could either pay me now or pay me later. We will very regularly say that to people. If you prevent it before it happens, it's all the best. In-process detection before it escapes your process is building it in. So you prevent it, mistake proof it. Don't even give it a chance to show up. But in the process, have anybody on the line stop that process from putting any more defective products or services out. You could do this end of the process inspection, not desirable at all. This is desirable. This is preferable. And then if at the end of the day, the only way the thing hits the wall is that the customer rejected your product or service and not what you want, it's way too late. This is actually too late. After the fact, you go test a lot of the things. No. So the sooner you catch the error, the better it is in terms of quality. Standard work, we did the pig diagram before, and I mentioned to you the difference between standard operating procedures and standard work. So we won't have to cover this because we played around with the pig diagram, and I think you guys have that. I think that's it, guys. Any questions? That was a lot, huh? That was more than last time.
I don't have any questions, but I've made some good notes that I think are going to be very helpful in the conversations with clients, especially when you're pulling PAs.
Oh yeah, they love it. PAs love it.
Yeah, so I think this has been really, and then also just some ideas around the fishboning and part of the SINDAG process, because I think part of the issue when you're trying to use that spreadsheet is columns 1, 2, and 3 can sort of sometimes not look like they apply to 4, 5, but I think fishboning might help that. So that's really good.
Cool. And as always, I mean, quality, the delivery, cost, and quality, cycle time. This last slide, I didn't spend much time on it, but it's important. Cycle time. If we want to reduce cycle time. Anyway, I guess, Jaime, I'll give it back to you. We could wrap up.
I think he's left.
Oh, did he? Okay. All right. Well, then, I guess I'll...
No. Jaime is there, I believe.
Where? Is he?
No, I don't see him. You're right.
All right. Well, all right. So, well, I'll just, I'll start, and Jorge, why don't we give you the last word, all right? So, I feel
Teacher's
good.
pet.
Teacher's pet. I feel good. I appreciate you guys taking the time out of your busy schedules, particularly on the weekend, to listen to these lectures. And I am going to load up a few things I think to help complement today's session. The quality is a heavy lift, so I'm particularly happy you guys hung in there. So thank you. Shridhar?
Okay, for a person who's more P and E like me, revisiting processes which are A is little what do you call patience testing, but good. It's good because it's just gives some ideas. There are some dots that have been picked up. I'll have to connect those. That's the only thing. That will happen only during incubation after such a downloading. It's good to be in this. Okay, it'll help in more ways than one. Okay, look forward to the next session now. Vladimir, should I pass it to Vladimir or Don? Yeah.
Hey, hello guys, can you hear me?
Yes, we can
Yeah.
see you.
Yeah. So appreciate for a great session. Me as a big A, I certainly like systems and a lot of quality as much as possible. But I understand that it's not always the worst that matters. But these tools, Daryl, that you gave us are really nice ones to explain, justify, and show how far the quality can go and to understand which quality you're after. So thank you very much. Appreciate it. Who's next?
Don, I believe.
Okay. Yeah, no, it's been really great. I'm glad I stayed up and attended. I think there's some really good things here, not only from an operational delivery point of view, but again, differentiating our marketing message. So I look forward to building some of those ideas and sharing with others. So really good. Thank you, Daryl.
Jaime just sent me a message that he lost internet connection, so that's why he logged off automatically. But I want to thank you, Daryl, again for a great session. Like the Adizes EP training, this is like a fire hose of information, and you want to drink from it, But it's great, and I like how many instruments or tools can bond or are able to work perfectly with Adizes. Definitely, I need to, during the week, reread all the slides you send us, because, I mean, it's too much to keep in mind just in one session. But thank you again. And who's next? Oh, that's it.
Good. All right, guys. A couple other folks dropped off, so thank everybody.
Bye.
Bye-bye.
Bye then.